All right, so today we're going to be looking at applications of quadratics. At this point, we have figured out most of the ways of dealing with quadratic relations. Now what we're going to do is applying them to real-world examples. So types of questions that you're going to find relating to quadratic relations are you're going to be finding zeros, either from a graph or an equation. You're going to be determining coordinates of vertex. You're going to be identifying the equation of a quadratic relation from its graph, and solving quadratic equations and sketching graphs. So some of the skills you're going to need to be having when you're solving anything related to quadratics. We need to be able to expand, we need to be able to factor, need to be able to complete the square, use a quadratic formula, and apply inverse relations. So those are your main informations. There's three types of problems that you may encounter when you're working with quadratic relations. One is when you're given a value of the independent variable, x, and then you need to determine what the dependent variable is. That's your y. Another example is when you're given a dependent variable, so your y, and then you have to go and solve for the independent variable. And the third type of problem you're going to find is when you need to find the maximum or minimum value of a dependent variable. So what that means, you need to find the vertex. So problem type A, you got your independent variable and you need to go solve for your dependent variable. That one's pretty straightforward. You're going to sub in your independent variable into the relation and just solve. Type 2, you're given a dependent variable, your y, and you need to solve for your independent variable, your x. So you're going to substitute in your dependent variable into the relation and then solve the quadratic equation. So you can either do that by factoring, applying inverse relations, or using the quadratic formula. And the last one is finding the maximum or minimum values of the dependent variable, which is your y of your vertex. So you need to go find your vertex, and that can be done by factoring and using the zeros to find your vertex, or by completing the square to get your equation into vertex form. So this first video is going to focus on the first three examples of your lesson, and then the second video will work on the last three. So looking at this first example, we have a ball that was kicked and its height represented by h in meters above the ground after time t in seconds is represented by the following equation. H equals 0.5 plus 16t minus 2t squared. First thing we want to do right off the bat is rearrange the equation into ax plus bx plus c format, which is what I did here. So h really is equal to negative 2t squared plus 16t plus 0.5. Here's a little graph here, quick little representation of what it would look like. It's going to have initial value at 0.5, and it's going to hit the ground at some point, and there's a maximum at some point. Kind of already answered the first question. What is the initial height of the ball? The initial height is represented by our c value in the equation, and our c value in the equation is 0.5. Our height is represented in meters, so we can say, therefore, the initial value, or initial height, let's switch that to height. The initial height is 0.5 meters, and we just got that from our c, this guy right here. Remember, the c is always our y-intercept, and for a lot of these questions where it's asking us for height or initial spot of the graph or the initial time, that's always going to be our y-axis, our y-intercept. Next question it's asking is, what time did the ball reach its maximum height? What that's asking us for is its time. That's the key word there. Time reached its maximum height. So that's going to be our AOS, our axis of symmetry. So it's asking us what point on the x-axis, or in this case our t-axis, does this equation reach its maximum height. So that's the x value of our vertex. So with this question here, our best option to find out our vertex or that AOS point is going to be to complete the square. So what we're going to do is complete the square. So H equals, we're going to pull out the greatest common factor from the 2 points. Remember, this is completing the square. We take it just out of the AX and the BX. We put the 0.5 on the outside. We need to get our new C. So we're going to take our new B, which is -8. We put that into things, so we get -8 divided by 2 squared, which gives us -4 squared, which equals +16. So we have +16 minus 16 in our bracket. Next up, what we're going to do is kick that -16 out of our bracket, leaving us with a perfect square trinomial in the center. Now, when we take -16 out, we multiply it by -2, which gives us +32 plus 0.5. Now we're going to factor this perfect trinomial. We can see over here is our -4 is going to go into the box. So we're going to open our bracket, x minus 4 squared plus 32.5. So our AOS is the x value of our vertex. Now our vertex in this case is going to be 4, 32.5. But our t, that x value, so our going to be t equals 4. So at 4 seconds, the ball reaches its maximum height. So therefore, ball reaches its max height at 4 seconds. What is the maximum height? That's the optimum value. Now, if you remember back to our first lesson, the optimum value is the y value of our vertex. If we go back here, the y value of our vertex is right here. It's our k, so our 32.5. So we can say now, from that information, therefore, the max height reached is 32.5 meters. Okay, that's our first part. That's looking at our maximums. That's looking at our example 3. That's our third type of problem. This one's now asking us for what time did the ball hit 0. The ball is going to hit the ground when height is 0. So that's really important to know. When the ball hits the ground, h is equal to 0. Our height is equal to 0. So that means we're going to be solving our equation for when it equals to 0. So when the height is 0. So we make our equation equal to 0. So what it's saying is we're going to go find our zeros or our roots. In this case, we're going to use our quadratic formula. So our A in this case is going to be -2. Our B is +16. And our C is 0.5. So let's set up this equation. T equals -16 plus minus the square root of 16 squared minus 4 bracket -2 bracket 0.5. And this is all over 2 bracket -2. Now, if we put this all into equation and solve for 2 different t's, we're going to get t1 equaling negative 0.3 seconds. This we can dismiss. The reason we can dismiss it is you can't have a negative time. Negative time to us makes no sense. We can't go back in time to a point before we kick the ball. Just doesn't work. Our second t value is 8.03 seconds. Now that we can use. That is a time in the future. So that's a future time in which the ball is going to hit the ground. So we can say the ball hits the ground at approximately 8.3 seconds. So this would be our therefore statement. Therefore, the ball lands at approximately 8.03 seconds. Now, the next question it's asking us is, when did the ball reach a height of 25 meters? So this question is asking us to find the point in which the ball has a height of 25 meters. Remember, our equation is h equals -2t squared plus 16t plus 0.5. We're looking for the point in which the height is 25. Now, if you think back to some of the practice questions that we've done, when we had something on this side here, on our left side, and it wasn't equal to 0, what we did was we brought that over to the other side to make the equation equal to 0. So that's what we're going to do here. We're going to make it equal to 0 on this side by putting the 25 on the other side. And since it was positive on one side, we're going to make it negative on the other. So we're going to minus 25 here. That's going to give us 0 equals -2t squared plus 16t minus 24.5. At this point, what we're going to do is take this information and put it into our quadratic formula to find the points in which this new equation equals to 0. And that is going to be the points in which the ball reaches 25 meters in height. So t is going to equal to -16 plus minus the square root of 16 squared minus 4 times by -2 times by -24.5. And this all is over 2 bracket 2, -2. Going up here and we solve it, we're going to have our first t equaling to 2.06. That represents on the way up. So on the way up, as the ball is going up in the air, it's going to reach a height of 25 meters at 2.06 seconds on the way up. Our second point, so our T2, is going to equal to 5.94 seconds. And that represents the way down. So it's reached its max height, and now afterwards it's taking its sweet old time to get back to the ground. That's on the way down. So to sum up, we can say that, therefore, the ball reaches a height of 25 meters at 2.06 seconds and 5 0.94 seconds. So that's a couple different ways of which we hit all the questions that are available to us. So let's look at this next question here. Lila is creating a dog run for her kennel. She can afford 30 meters of chain link fence. So 30 meters is how much fence she can have to surround 4 dog runs. The runs will be attached to a wall, therefore she will need no fencing on that side. To achieve maximum area, what dimensions should Lila use for each run combined? So we want to know what dimensions for each run and for the combined enclosure. So here's a diagram of her run. She has a wall on this side, and here are her 4 lanes. You're going to have a chain link fence here, 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 and here, and a chain link fence on the end. Like any question where we're not given any letters to represent information, we need to make our own. We need to have a let statement. So what we're going to start off by doing is saying let W rep the width and length is going to be represented by something else. So I'm going to leave that blank for a minute. If we have W and we're looking at creating this information, we're going to have W here, a width here, a width here, and a width here, and a width here. We have 5 of them. 1, 2, 3, 4, 5. So the fence that is going to be here can only be represented by one thing. So this is our length. And our length is going to be represented by the total amount of chain link fence that you can have, which is 30 meters of fencing. Subtract these 5 widths here. So minus 5W. So that's what length is going to represent. Length is going to be represented by 30 minus 5W. Now she wants to maximize the area. Our area here is represented by length times width. Our length, in this case, we represent as 30 minus 5W, and W is simply W. What we're going to do now is we can expand this. If we expand this, we end up getting 30W minus 5W squared. So this right now is in standard form. If we want to find out the dimensions to find out the maximum area, we need to have this in a format that gives us the maximum and gives us our vertex. We need to find out the vertex. The vertex tells us the maximum. So what we need to do is we need to find the vertex. We need the vertex. And how do we find out the vertex? Well, we go and find vertex form. So let's rearrange it so we can see it in the nice proper order. A wonderful standard form. What we always do when we are going and finding our vertex, we're going to use completing the square. It's the fastest way to do this. So what we're going to do right now is pull out the A from both points, which is negative 5. So we get 5W minus 6W. We're going to leave a space for our new C. So our new C is equal to our B divided by 2 squared. So we get -6 divided by 2 squared, which gives us -3 squared, which gives us 9. And we're going to add 9 and subtract 9. All right, now we want the inside here to be a perfect square trinomial. So that means this -9 needs to get out. And as it's getting out, it's going to be multiplied by that -5. So we get 5w minus 6w plus 9. -9 times by -5 gives us positive 45. And we end up getting -5 bracket w minus 3 squared plus 45. So that means our vertex is 3 and 45. Now it's important to be able to identify what each of these informations mean. This 3 here represents our width. That is the width that can be possible at our maximized area. And this right here, this 45 is our maximized area that can be reached. So what that means is that the length of the enclosure is going to be, with each of these 5 rows being 3. And then we need to figure out what our length is. So our length is equal to 30 minus 5 bracket 3. 30 minus 3 times 5 times 3 gives us -15. So, yep. And then that's going to equal 15. Meaning this entire length here is 15. But there are 4 runs. Remember, it's asking us for each run what the enclosure is going to be. So that means we need to take this 15 and divide it by 3. So 15, not 3, divided by 4 is going to give us 3.75 meters. Therefore, what we can say is that each run is going to be 3.7 meters. Should write that as a sentence, sorry about that. Therefore, each run will have a dimension of 3 meters by 3.75 meters. Just so you guys can see this is going to be 3 meters, and right here is going to be 3.75. That's the dimensions of each run. Let's move on to the next question. Example 3. Grace hits a golf ball that follows a parabolic path because it's a great shot and it's just perfectly parabolic path. The ball lands at 120 meters from where the ball was struck. The ball was 40 meters above the ground when it was 20 meters short of the hole. What we're going to start off with is drawing a diagram that models the flight of the ball. So I've already kind of drawn one out here. What we're going to notice is that the ball struck from the ground. So that means it struck here at 0, 0. That's our first point. That's our first information. This line here, this axis, is going to be our horizontal distance, meaning this is how far it has gone. Now the one up here, our vertical, is going to be our height. And that's represented by meters as well. So if we're looking at this, the next information we found is that the ball lands 120 meters from where it's struck. So it's gone and hits the ground at 0, at 120, and 0. At some point in its path, when it hits 20 meters from the hole, which means that it's not at 100, it's at a horizontal distance, no, sorry, it's not at 120, it's at a horizontal distance of 100. It's at a height, though, of 40 meters. So I'm just going to put like a little arbitrary distance. This looks about right. This is at 140. So if you notice from this graph, these are our two zeros. These can be our R and our S. Good point to remember. What we're going to do now is determine an equation that models the flight of the ball. So this one's set up perfectly that we can create a factored form equation. So we have height equaling A bracket X minus R X minus S. Our first zero that we have is, well, 0. So we can put that in the R spot. So let's put that in now. We have A equals X minus 0. Our second point, our second 0, is at 120. So S is going to be now replaced with 120. If we rewrite that, what it looks like is A equals X times X minus 120. So we still have an unknown variable here. We don't know what this A is. So how do we find that out? We're going to now take this second point that they gave us, and we're going to sub in that point. So we're going to sub in 140. So the 40 goes where the H is. 100 goes where all the X's are. At this point, we're going to we're going to simplify and solve for A. So what we end up getting is 40 equals A times by 100 times by negative 20. So we get negative 2,000 A equals 40. We're going to divide both of these sides by negative 2,000. And what you get for A is negative 1 over 50. So what we want to now do is bring all that information. So we're going to have, therefore, our height is equal to negative 150, that's our A, negative 1 over 50 X, that's our first X right here, and then we're going to bring in our second bracket, X minus 120. So that is our equation. Now what we want to do is, what was the maximum height of the ball? The maximum height of the ball would be the AOS, would be at the AOS. So that means we need to find out the vertex. We right now have a equation that is in factored form. It would make no sense for us to go backwards to get our standard form and then go complete the square. For us at this point, it's better to find the AOS and then the optimum value, aka our y. So that's what we're going to do. I'm going to first find our AOS. Remember that our two zeros are x equals to 0 and x equals to 120. We found that out when we graphed it all the way up here. So our AOS is going to be x equals 0 plus 120 divided by 2, which gives us 60 for x. Now we're going to take that x and we're going to go find the optimum value. So we're subbing that x value into our equation. So h equals negative 1 over 50 times by 60 times by 60 minus 120. And that gives us 72. This number right here, this 72, is our maximum height of the golf ball. So we can say, therefore, max height, the golf ball reached, was 72 meters. All right, so that's the first 3 of our problem solving questions. Come back for video 2 of our next 3.